Right, so chapter 9, I've labeled it in the notes as iterative methods. Okay, they're also called indirect methods. So if you hear me talk about iterative methods or indirect methods, I mean the same thing. Okay, indirect methods tends to be to be honest, the better name for them. And as I mentioned, this is on chapter 9. Right, the methods we've covered so far. So if you think of what we've done so far this term in this unit, Gaussian elimination. Well, you've done that previously. LU, LUP, and Cholesky factorization. These are known as direct methods. So in other words, a direct method is when you just have one application of the method will give you a solution. There are issues with direct methods. The second bullet point down on that slide, no way of improving the solution using a direct method. So far, we've looked at quite easy, small systems. In real life, when we're solving ODEs, they're not going to be small, easy, whole number systems. So you're always going to introduce some form of computational error there. Now, with a direct method, a single application gives you the solution. That solution you have, there's no way of improving it. That's your lot. So if your solution does suffer from a bit of computational rounding, tough. That's all you have. Indirect methods, what they do is they use a series of iterations to continually, hopefully improve the solution until a required accuracy is obtained. So direct methods, you just apply once. Indirect methods, you apply in iterations over and over again until you get your solution. Indirect methods are much more useful for larger systems. You'll be doing, your sparse matrix calculations with leader. What tends to happen with direct methods is you do tend to have sparse matrices. Indirect methods are far more efficient, use less memory, especially when you have large systems, which we tend to have when we're doing this in practice. Okay, so those are the two methods. The ones you looked at so far are direct. We're going to be looking at indirect. Okay, and the first one, I think you've probably seen before, actually. Jacobi method. Okay, the simplest indirect method. What we have is, let's say we have a linear system of this form. And you should sort of recognize this form. The A's are some coefficients. The X's are the unknowns. And on the right-hand side, we have B's, which are known value, right-hand side values. So A's and B's are known, X's are what you want to find out. So if you can take each row, okay, each of these equations, what we can do is we can solve it for the ith term. So for the first row, we can rearrange that to solve for x1. The second row, we can rearrange and solve for x2, and so on and so forth. So if we do that, we get a series of expressions in both, so x1, x2, x3, etc. So if we take the x1 to start with, okay, so essentially we have the reciprocal of the coefficient of x1, so 1 over a11, b1, and then we have minus all of the other terms in that first equation. Okay, so in order to calculate x1, we need to know what x2, x3, x4, etc. are. And similar thing for x2. Okay, if we rearrange x2, we get 1 over a22, b2 minus, well, for x2, we have an x1 term. And then, of course, we've already got the x2 term there. And then we have the x3 term, etc. Okay, so all of those equations down here, on the right-hand side, they involve values for x. But x is our solution. We don't know what it is to start with. So what we do is we assume some values for your x's. I usually use 0. And if we calculate each of these through, we'll get an improved estimate of our solution. It'll be rubbish, but it will be an improvement. And then we can take that solution and calculate them all again, and we get a better estimate. And we keep going until we get a pretty good or as good as we need it to be. Okay, we could write this using summation notation. So this is for the ith value of x. The notation I'm going to use here is the superscript denotes the iteration. Okay, so I've actually put my superscripts in brackets just to show you they're not powers, they're not exponents. The superscript just say, okay, that's the kth iteration. The subscript I means whatever the ith value of x is. Okay, so for the Jacobi method, we have the reciprocal of the main diagonal of the coefficient matrix. You have the right hand side value b, and then we have summation. Now the summation goes across for all values of x except the ith value. So j is our summation counter. So j goes from 1 to n that we miss out when j equals I. Okay, so that's a little bit of notation there just to be aware of. Okay, that's the Jacobi method. One thing to be aware of is in order for this to converge to a solution, and we'll look at that later about convergence, we need diagonal dominance. Okay, so the coefficient matrix is assumed to be diagonally dominant. That means the absolute value of the main diagonal element is greater or equal to the sum of the